Hello everyone, my name is Pulak Sarangi and I'm a PhD student in the Smart Sensing and Information Processing Lab headed by Professor Piya. So our lab primarily focuses on the mathematical and algorithmic foundations of signal processing and data science. So I would try to briefly cover the main research themes that our group is currently focusing on. The first topic is about spatiotemporal computational sensing with sparse arrays. So in this topic, our focus is on understanding how do we place our sensors to measure a given signal. In a variety of estimation problems, if we move away from the conventional way of uniformly placing our sensors, if we adopt a sparse strategy to place our sensors, then we can often achieve more with the same sensor budget. Once we have sensed our signal using this unconventional sensing geometry, now we have to computationally recover our signal of interest. And this is what gives rise to inverse problems. So this idea of designing sensor geometries is extremely relevant in the context of target localization using radar or sonar, and even in the context of millimeter wave communications, where we have to decide how do we place our antennas that is eventually going to shape the effective channel. Now moving on to solving these high-dimensional inverse problems. So as mentioned earlier, often we are interested in recovering a high-dimensional signal, but we only observe a distorted version of the signal through some measurement map. And often the number of measurements that we have are limited. So our goal is to reconstruct this original signal from these limited measurements. And often these problems are ill-posed, and we have to exploit suitable types of priors to be able to perform this reconstruction. So one of the main goals is to understand how many measurements do we require to perform this reconstruction. And the second question is how to design computationally efficient algorithms that can enforce these priors on our desired signal. The third topic is about correlation-aware sparse signal processing. So we have shown that by exploiting the additional correlation structure present in the data, in addition to sparsity, we can operate in compression regimes which is much higher than simply relying on sparsity-based techniques. And finally, we also work on understanding the fundamental limits of super resolution. So in super resolution, there is an interplay between what kind of sensing geometry that we use and what are the type of priors that we use. So we show that fundamentally it is possible to achieve much better performance by using certain types of priors such as non-negativity, correlation, or binary priors, which are extremely relevant for super resolution. In addition to these theoretical problems, we also actively collaborate with people in neuroscience and radiology. So in one of our projects, we apply the idea of computational uh, compressive sensing for cellular MRI to develop new sampling strategies. In our collaborative project with the neuroscience department, we developed new super resolution algorithm to decode the spiking activity of neurons from calcium imaging data. Thank you.
For more information, please visit ece.ucsd.edu.